So, hi everybody, welcome to the heap data structure now. This session is all going to be about the heap. First, we're going to talk about the heap data structure itself, and then we're going to talk about the heap source. So that's going to be a part of the chapter 23, which we already covered, but we stop at heap. The heap is also a type of a tree data structure. It's a great and efficient data structure that can be used for sorting algorithms and the priority queue implementation. So the heap, as you can see, is a binary tree, and but it has its own properties. So the two main property of the heap is that the heap should be a complete binary tree. So the complete binary tree is different from just a binary tree, right? So if you remember in the binary search tree, we had level by level as we fill the data. They can sometimes be levels that are not full, and something in the middle of it is complete. But when we're talking about the complete binary search, means that all the levels are going to be completely full before we go to the next level. And as we adding element to the level, it's always going to go from the left to the right on each level. So that has to be in order that we adding element. You cannot just add element based on to any part of the tree. So this particular property make this tree always be balanced, because you're not going to go to the next level if the previous level is not completed, and we're always going to start from the left. So anything else we talk about a binary tree is valid, that this is a specific type, and it needs to also on the top of all of them be a complete binary tree. Another important thing about it is that each node should be greater or equal to any of its children. So that basically we're making kind of like a max heap, that the root is always going to be the maximum element of this at this tree. And that's how you can imagine this data structure is going to be used for heap sort. You can, instead of max heap, you can create min heap, right? So it's going to be exactly opposite feature in it, and then that's going to create the min heap, and then that can be used for ordering in a natural order, or max heap is going to be ordered for ordering from the largest element to a small. So you have to maintain these two properties. So let's see what we mean by a complete binary search tree. So look at the examples that we have done at the bottom of the page. The first one is a tree that has 0, 1, 2 levels basically, right? And in every levels, all the nodes possible, it's available. So it's completely complete tree. So this is a complete binary tree. Is it a heap or not? So he has two properties. First, it has to be complete. So this one is complete, but is it a heap or not? So the heap should be every single node that we look at, it should be larger than its children or equal. So you can't have duplicates. So 42 is bigger than 32 and 39. 32 is bigger than 22 and 29, and 39 is bigger than 14 and 33. So this is not only a complete tree, but also is a heap. So the very first one is heap. Second one, is it a complete tree or not? And the answer is yes. Why? Because although we have some element missing on the very last level, but the level is started to fill out from the left to the right. So the very right one only is not available. So this is a complete tree. Now let's see if it's a heap or not. 39 is less than 42. So that's not a heap. It's a complete tree, complete binary tree, but it's not heap, because there is a node that is smaller than its child. So it's not a heap. Next one, is it a complete tree? No. And the answer is, what the reason is, in the last level, suddenly in the middle of this level, there are things that are empty. It has to be complete from left to the right, and this is not. So this is not even a complete tree. So we don't even have to go to checking the second property but we know already the first one failed. And the next one, it definitely is not a complete tree. You don't even have the half of this other part of the tree. So you're missing completely the level 1 and most of the level 2. So this is definitely not a complete. So you have to finish a layer completely a level before you can start the next level. So this is definitely is not a complete binary tree. So we don't even have to check the second property of the heap. So how are we representing the heap? If you remember, in binary search tree, we represent that using linked list structure. But heap, we're representing it using array list, actually. So we're storing data in the array. Why? Because the element at the index 0 is basically your root, as you can see. You see the mapping here. Then we're always going to start from left child and we go to the right child. So we only can have 2 child for the root. So that's going to be index 1 and index 2. The left child is going to be index 1 and the right child is going to be index 2. And then when we start the next level, we definitely have to start from the most left one. So the left side, the left child, and that's going to be here is 32. Then we have to go with one by one, fill the entire level 4 from left, sorry, level 2 from left to the right. So I have to first go to 32, then 39, then 45, 44, and then 13. So the index of those are clear. So 0 is the root, 1 and 2 are the children of the root, 3 and 4 are children of the index 1, and 5 and 6 are the children of index 2. So when we get to the next level, first we have to go to the index number 7. So 7, 8, 9, 10, and so on. So it's going to be exactly map on an array list with the index 0 to whatever number of element is. And you can actually calculate every time. For every node, you can calculate who is their parent and who is their left and right children if they do have anything. This is the formula that we can use to calculate the child for each node. So if I go to index 0, the children of index 0 are going to be index 1 and 2 based on this formula. So the left child is 2i plus 1, and the right child is 2i plus 2. So if I go to 7, for example, 14 plus 2, and 14 plus 1. So 15 and 16 going to be the children of 7, and it doesn't have any children at this point, right? So but we want to have any children for it later on, they're going to be found in those two indexes. So right now, this area only have 12 elements. This index has, or this heap structure only have 12 element in it. If I want to add one more, definitely I know that that new element has to go inside the index 14. That's for sure. But if we just randomly add it, what if that the new node that I added to this index is going to be bigger than 13? So if I have 42, then what's going to happen? So as you can see, if I do that, although this is going to stay as a complete tree, but no longer is going to be the heap, because now you have a node that is less than its children. So you cannot just go ahead and add element in the index that you know it belongs to that index. You have to do other things. We call that other things the heapify method. So basically you have to now swapping things around a little bit, so you can find the actual location of the new element that you add without breaking the property of being complete tree and without the breaking of the property of being heap. So how are we going to do that? In this to showing this, what I have to do is to use a the whiteboard here, and then I'm going to try to illustrate what we have to in this picture. So we first starting with an empty heap, and then we start adding elements. So and as we add element, I'll explain the heapify method. So I'm going to do same example, but in this slide, you don't see the entire steps. You just see the final result. So we're going to show you the entire step as well. So let me share a whiteboard now. In the whiteboard, I'm going to start, I guess, by drawing. You have to, guys, bear with my drawing. I'm going to start drawing this trees. Oh, let me do it this another way. So this is not going to work. Yeah, I'm just going to draw them. Hopefully that's helpful. Oh, by the way, there is empty at the beginning. Sorry. So we have a heap that is empty at the beginning. I forgot about that fact. So we're going to add the very first element, and that's 3. So this, since nothing is in this heap, and we're trying to add 3, so that's become our only element, and that's going to be the kind of like our root, right? So it's going to go to index 0. So I'm drawing here the array list. Oops. And over there, I'm going to add the element. So adding 3 to the, it's easy. Just it's going to go to the index 0, and there's no other place for it to go. So this is our index. Then we're going to add our next element. So the next element is 5. So the only place that this 5 can go is going to be index 1. So that means it's going to be the left child of this 3. But so this keeps a complete 3, but the problem with this is that now it's no longer a heap, because now you have a children that is bigger than its father. So that's not a heap. So how are we going to do that? At this moment, we're going to call the heapify. How many times we have to call the heapify for solving this problem? Only one time. So that means we're only going to go through just one swapping. And what we're going to do, we're comparing 5 and 3. And since, which is the father and child, and since the child is bigger than his father, we're going to do the swapping. So that means this has become 3, and this has become 5. So after calling the heapify, this 3 is going to switch to this 3. So that's the 5 on the top, and then 3 is coming here. So the array list, as you can see also, is going to be the 5 in the root, and 3 is going to be in the index 1. Next element that we're trying to add is going to be 1. So the only place that I can add 1 is the right child here, which is going to be also the index 2. That's the only place I can add it. So we're adding it to the index 2, and we check if it's a complete 3. Yes. Is it a hippie? It doesn't need any heapify or any swapping. No. Why? Because the parents is bigger than all the children. So sometimes we need heapify, or sometimes we don't. Next element we're going to add is 19.